Good afternoon. So we have a new day, new theme. Today we have a presentation from Dr. Sajjad Ahmed about pulsed IV characterization. Yeah, happy that you joined us today again. I see some names that are familiar in the meantime. Dr. Sajjad Ahmed, he finished his university and he made his degree in France at Aix-Lim. He has experience also here from Europe and worked and lived a couple of years here in, I think in Munich, right?
Yes, yes.
Okay, wonderful. Good location. He's back in Canada now and he's in charge of business development management at Focus Microwave. And he's well, one of the real experts in load pull measurement. So thank you, and well, it's yours.
Okay. Thank you, Rola. So should I start or should I wait for some time?
Well, I see some people still coming in.
Okay.
I would say we have 3 o'clock here European time, 1 minute past the hour. So let's start.
One remark maybe. If you have questions, you can put them in the chat window, and I will collect them. And we will look through the questions at the end, after the presentation together. Go ahead, Sajjad.
Okay, thank you. Thank you, Roland. Thank you, Remy. So my name is Dr. Sajjad, and I'm the Business Development Manager here at Focus Microwaves. So I'll be talking about some pulsed IV characterization today. So actually, I'll close my camera for now. Yeah. Okay. So let's start. So my talk will include some basics of IV characterization. Then I'll be talking about some pulse signal and why is it important when we are talking about IV characterization, some high power applications using pulsed IV, the pulsed S parameters, and the introduction to compact modeling. So IV characterization or IV characteristic curves. Now, as the name suggests, so this is basically the relationship between the current flowing through an electronic circuit and the voltage applied across its terminals. Now, IV characteristic curves are generally used as a tool to determine and understand the basic parameters of a component or a device. And this information can also be used to mathematically model its behavior within an electronic circuit. Now, in the represented circuit here, if we see, if a voltage V applied across the resistive element R is varied, we can determine the current flowing into the circuit. So this current voltage relationship is basically computed using the simple Ohm's law. Now, as we can see, if the resistor within this circuit is a fixed value or is kept constant, the resulting curve, which can be graphically represented, is a linear value, which means it is a straight line. But when we are talking about advanced electronic components, the relationship between the voltage and current is no more linear, which means that it's not a straight line. So let's take an example of semiconductor devices. So semiconductors such as diodes or transistors, they're all constructed using PN junctions. And if we want to have their IV characteristics, they will basically reflect the operation of these PN junctions. The circuit represented here is an E MOSFET, and it's a 3-terminal device. So if we want to characterize or have the IV characterization of this circuit, so one of the terminals is kept constant. For example, here, if we see, so the VGS is kept constant and the V drain source is linearly varied. And we have the resulting drain current. Now, looking into this curve, we see that it can be divided into two regions, the ohmic region and the saturation region. In the linear region, which is the ohmic region, the conduction channel basically acts like a resistor. So if we continue to increase the voltage, the channel potential will reduce the current, and we will get to a point where we no longer see any change in this current. This region is called the saturation region. Now, for typical IV measurements, this measurement is repeated for multiple gate voltages, and we have the final IV characteristics of that device. Other IV tests may also include some transfer characteristic measurements. Now, transfer characteristic measurements is the relationship between the gate source voltage and the drain current, where VDS is kept constant. So in DC IV measurements, basically a series of voltage varied over time is applied to the device. And at 8 voltage, the current flowing through the device is measured. This continuous cycle increases the device temperature. Now, due to this change in temperature, or due to the rise in temperature within the device, the device parameters or the transistor parameters will have a slightly different response. And they might exhibit memory of the previous signal, which means it might be dependent upon whatever state it was at previous voltage levels. So this behavior is also termed as thermal memory. And of course, it's an undesired behavior. So when we look into the DC IV curves of a transistor, we see that in the saturation region, the current decreases. Now, this is why the reason for this is the bulk temperature within the device starts increasing, which affects the mobility of carriers in the channel, and it decreases the flow of current into the device. Now, to avoid these thermal effects, basically a pulsed DC characterization is a preferred method for IV characterization. So what is a pulse signal? So a pulsed signal is basically the bias point for both gate and drain that goes through a rapid transient change in voltage amplitudes starting from a base value. And it's a periodic signal, which means it repeats itself. And for a pulse signal, the two parameters that the user can control are pulse width and the pulse period. And the two dependent parameters based on these two parameters are the duty cycle, which is basically the relationship between, or it's the ratio between the pulse width and the time period, and it's represented as a percentage, and the pulse repetition frequency, which is directly dependent upon the pulse repetition rate, which is the pulse period. So when we are talking about pulsed IV characterization, it's always desired that the pulse width is kept very, very small, so that the thermal time constant is much less than the thermal effects happening within the device. But here, if we see that even if we keep the pulse width very small and the pulse repetition frequency is high, we see that the temperature between pulse to pulse keeps on increasing, which of course is not a good, which is not required, or which is not desired. So what is important is, on top of the narrow pulse width, we should also have a high time period. So which means that the pulse period should be much, much greater than the pulse width. In this case, if we see the temperature rising within, or temperature rising within one pulse does not effectively adds up to the next one. So this is why we call it a quasi-isothermal measurement. Now, how do we do the typical pulsed IV characteristics? So the static DC point for both gate and drain voltages on which the pulses are superimposed is referred to as the quiescent point. Now, this quiescent point basically determines the class of the amplifier it's operating on, and it also determines the thermal state of the transistor. Now, starting from this quiescent point for both gate and drain, we sweep the non-quiescent voltage amplitudes for the gate, and for each gate value, we perform a subsequent drain non-quiescent sweeps. And this measurement is repeated for multiple gate values. And finally, we have the complete IV characteristic or IV network of that particular device. So now, when we are talking about the recent industry's wide bandgap semiconductors, so in those devices, now temperature is not the only physical characteristics that give rise to dispersion effects within the devices. There is another effect that is called trapping effects, and which is often related to some malfunctioning of the materials. So these memory effects or these trapping effects are also responsible for short and long-term memory effects. So when we can control the different parameters in the pulsed IV characteristics, it enables us to determine basically the electron emission times related to the different regions within our IV network. For example, when we want to characterize gate lag, so we control the quiescent bias points of the drain voltage and we keep the non-quiescent voltage constant. Similarly, when we want to characterize the drain lag, we sweep the non-quiescent drain voltages and keep the gate quiescent voltages fixed. So for a good pulse IV system, we should have control over all the parameters within the pulse. So in this slide, I will be talking about some what is a pulsed IV measurement system. So here it represents the basic block diagram of the Auriga's 5th generation pulsed IV system. So a pulsed IV system basically consists of 3 building blocks: the pulse generation, digitizer, and the timing control. The pulse generation basically is are the fast switches that basically generate the pulses at both gate and drain. As we said, the pulse in pulse characterization, the pulse width can be very narrow, which means that the measurements or the settling time for the measurements is very, very slow. So we need to have fast measurement system. So that's why a fast digitizer is equipped within this system so that we can have good stable measurements within the pulse. And the third main, a very important block is the timing control. The timing control block is basically the fundamental controlling element for the digitizers and for the electronic switches that connect the 4 DC supplies to generate the quiescent and non-quiescent voltages. The 5th generation Auriga Pulse IV system basically is a fully featured characterization platform. It is capable of measuring the DC IV curves. You can measure the pulsed IV curves, and this system can be expanded to pulsed S parameter measurements and even pulsed load pull measurements. So when we are talking about pulsed IV characterization, so each application is specific to certain parameters. And the parameters could be the maximum and minimum voltage and current ratings. It could be maximum or the minimum specified pulse width, the maximum pulse repetition frequency, or the maximum output power. So Auriga offers a range of pulsar heads, both for gate and drain. For example, for gate, we offer 2 different heads, plus minus 20 volt 100 milliampere and the plus minus 100 volt 2 ampere head. Similarly, for the drain side, again, we offer a range of pulsar heads starting from 220 volt 2 ampere, and we go all the way to 2 kilovolt 100 amperes for high power applications. The pulse width can be as narrow as 200 nanoseconds, and the duty cycle within the system can be varied from 0.01% to 100%. The pulse repetition frequency again plays a very, very important role to quantify the emission time constant. So the pulse repetition frequency again is different for different pulsar heads, and The difference is why? Because it is related to the thermal dissipation within each head. So now talking about the quality of pulse that is generated using these pulsar heads. So theoretically, it is desired that in an ideal situation that the pulse turns on and off instantaneously. And right as it is turned on, we should achieve the maximum voltage that is set by the user. But in reality, that does not happen. There is always a rise and a fall time associated with the pulse. So this rise and fall time is basically, how long the pulse takes to reach its maximum value. A good pulsar is designed to minimize these fast rise and fall times. But there is another thing or another phenomena that is associated with these rise and fall times, which is the ripple. So the faster the rise time, the more the ripples are. And what are these ripples? These ripples are basically overshoot and undershoot. And overshoot is defined, it's a voltage level that exceeds your target level right after the pulse is turned on. Similarly, after that, it goes below the target value and it comes back. So it kind of oscillates before it settles down. So this oscillation period is called ripple. And it is directly related to how fast your pulsar turns on. So the faster the rise time, the faster the ripple. And if we have a huge ripple within the pulse, it means that the measurement time or the stable time within the pulse becomes very, very short. And we won't have enough time to make good stable measurements within the pulse. So for a good pulsar head, for a good system, it is desired to have minimal ripple and the maximum possible rise and fall times. So this slide represents a typical pulse generated by the Auriga measurement system. Here we can see that the effective rise and fall time is around 50 nanoseconds for this pulsar head. And here we see that the pulse is pretty clean. So there is minimal ripple, there is minimal overshoot. And this of course is required. Why? If we have a very clean pulse, we can make measurements much closer to the transient state, so which gives us better isothermal measurements. And it also gives us a wider sampling time so that we can have a good average signal within the pulse. Now, as the pulse width becomes narrow, so here it's represented at 200 nanosecond pulse width, we'll see that we'll end up with a rounded kind of a shape. This is why the reason for this is that the rise and the fall time of the pulsar head is around 50 nanoseconds, which means that we have a very small measurement window within the pulse. So if this pulse is not clean and we have some ripples and overshoots here, the measurement within this pulse will not be stable. Now, when we are talking about IV sweeps, there is another important point that we need to take care of is when defining the pulse timings for our measurement system. So Auriga allows to set multiple different settings and different delays for both gate and the drain pulsars. And it also allows you to control the quiescent and non-quiescent voltages within these pulsar heads. Now, when we are talking about the IV sweep settings of the pulse, there can be certain cases where the gate and the drain pulses are not of equal weight, that we might create some intermediate stages which are neither quiescent nor non-quiescent state. Now, usually these intermediate states are not harmful, but there could be a condition where the intermediate stage can be destructive to the DUT. The following analysis will explain how these intermediate states occur and why they need to be understood. So we'll talk about two different scenarios. The first one is where the quiescent drain voltage is less than the non-quiescent drain voltage. So here we see that we have the gate pulse and the drain pulse. So the quiescent for the drain voltage is lower than the non-quiescent voltage. And again, the drain pulse is narrower than the gate pulse, which means that the gate pulse turns on first. Now, here we see that starting from the quiescent bias point, so where the quiescent current is flowing into the device, which is this region, we see that the gate non-quiescent pulse will turn on. It means we will create an intermediate stage, which is neither quiescent nor non-quiescent. So we'll jump to a new gate non-quiescent voltage before we really hit our target, which is the non-quiescent voltage for both gate and drain. So here you can see that we created this intermediate stage. But as far as this intermediate stage is within the safety settings of the system, this is not, it's benign, it's not harmful for the pulsed IV setup. Similarly, for the off state, again, we will jump to the intermediate stage and then back to the quiescent value. The second condition where what we will discuss is where the drain pulse is wider than the gate non-quiescent voltage, which means here that the drain non-quiescent will turn on first and then the gate non-quiescent. Again, here we see starting from a quiescent value, we will jump to a higher drain quiescent voltage, and then we will move to our target non-quiescent IV condition, IV set target. The third condition is where we have the gate and the drain pulses of equal weights. So here actually we don't create any intermediate stage and we directly jump from our quiescent to our target value. The second condition here that we will discuss and this is the condition where we can have some problems. This is the condition where the quiescent drain voltage is greater than the non-quiescent drain voltage. So here we can see that the drain quiescent is at a very, very high level. So starting from the quiescent current, we see that drain is at a very high quiescent. If the gate non-quiescent turns on first, it means we will jump on to a higher gate value. And there could be certain conditions where we are beyond the safety settings of our system. Now, this is hazardous for the device. This can destroy the device. So this is, of course, not something that should be done. And then, we will shift, but this will never happen. So the idea here is when defining the time of the pulse, it's important that we take care of these intermediate stages. Though Auriga will not let the system go out of its safety setting as it will abort the measurements. So the device will be kept safe. For the other two cases where your gate pulse is narrower than the drain pulse, in that case, we create an intermediate stage, but that is much within the safety limits of our system. So it's benign. Similarly, when we have equal gate and drain pulses, again, we do not create any intermediate stage and we jump directly between our quiescent and a non-quiescent IV characteristics. So now as we were talking about the pulse quality, so when we are talking about the real measurement scenario, in the real measurement scenario, we do add some, adapters, connectors, bias tees between our pulsar head and our measurement reference plane, which is the DUT reference plane. So all these adapters, cables, and bias tees, they, add to some parasitic inductance, parasitic capacitance, and even the parasitic resistance. So this parasitic inductance and parasitic capacitance, basically, it adds to the overshoots. It increases the rise time of the pulse. And of course, because of the ripple, the settling time increases within the pulse. So which means if we have a narrow pulse, we might not even have a stable region within the pulse. Another important point here that should be discussed is that all the components, within the pulsar head, between the DC supplies and the output of the pulsar head, they do have certain resistivity, which means, because there are some wires, there is switch on resistance, there are some measurement resistors. So the addition of all these, parasitic resistors make the output impedance of this pulsar head. So this output impedance varies for different pulsar heads, and it is on the lower side. It is around 1 ohm, 2 ohm levels. Now, what happens that when current that is flowing through the output resistance of this circuit, it creates a voltage drop. So the measurement that is set at the power supplies, you might not see that voltage at the output of the pulsar head. But this does not affect your measurement as whatever, because all this offset is happening much before the measurement circuitry. So whatever is being measured by the circuit or measured by the digitizer is basically the true voltage that is being set at your measurement reference plane, or that is basically set at your DUT reference plane. So this offset does not affect your measurement. So the last point here that I will talk about is the parasitic resistance. So this parasitic resistance can always be calibrated out. How? So let's take an example here that for a measurement case here, between our device and our pulsar head, we have a cable, a bias tee, maybe some adapters, then again a cable until we reach our DUT reference plane. So for this path, we can always calculate the path resistance of this entire path. There are multiple methods available to calculate this input and output path resistance. So once these input and output resistances are known, we can define these resistance in our software, and then the software automatically compensates for this offset. So once we have defined these offsets, or once we have defined these resistance values, the voltage that the user sets at the power supply level is the voltage that you should measure at your measurement reference plane. Another method of doing similar measurements is that our software allows is called servo. Servo is basically an iterative process. So it means, it allows to very precisely set voltages, at your measurement reference plane. So when user sets a target value, it will be measured by the digitizer, and if it does not meet the target value, the software will reiterate and try to adjust its power supply so that it meets the target value at the measurement reference plane. Now, talking about the digitizer within the Auriga Pulse IV setup. So the digitizer basically, it returns the calibrated values across the portion of the waveform that is displayed on the scope. Now, this portion is, of course, set by the user, and usually, it is set within the stable region where the pulse becomes pretty stable. So for both non-quiescent portion of the pulse and the quiescent portion of the pulse. So these small segments are called basically the apertures. So we have both non-quiescent aperture and the quiescent aperture. And the final values that are displayed in the IV characteristic curve are basically the calibrated and averaged values within these time segments. Now, on top of the digitizer or the digital values that we see in the IV curves, Auriga is equipped with with an oscilloscope which has 16-bit resolution and a very fast sampling rate of 200 megahertz. So now this option allows to have complete time domain waveforms or time domain pulses for each measured IV curve. So what happens is here is, that the measurement signal can be plotted, versus time. So which allows us to notice any time varying changes occurring, that might occur due to self-heating or trapping. So we have the entire pulse shape, and we might see, in some cases that the pulse starts decreasing, or it might have some other effect. So the Auriga, because of the fast sampling rate of Auriga, we can view all these changes within our pulsar heads. Another enhanced measurement technique or a mode that Auriga offers is called measurement enhancement mode. Now, this feature basically is implemented because the fast scope that is part of the digitizer, that might undergo, some significant drift and jitters. So what MEM does is it uses a digital multimeter to correlate the jittery oscilloscope measurements with a very stable DMM digital multimeter measurements through very advanced calibration algorithms. So in the end, because of this mode, we get a very high resolution of current, which is around 0.01 of the maximum current. And we get very stable measurements for longer period of time. Now, when we are talking about, the emerging high power applications, so it is very important for a pulsed IV system, to withstand very large voltage and current ratings. And at the same time, fast switching speed is always desired. Now, to fulfill this requirement, the Auriga system offers again multiple heads that include 1200 volt 100 ampere, 1200 volt 10 ampere, or even 2 kilovolt 100 ampere head. These pulsar heads offer a minimum pulse width of around 1 microsecond and a rise and fall time of around 84 nanoseconds. These properties make these pulsar heads a very, very unique product presently available in the market. For high power applications, a very common test that is performed in the industry is called dynamic on resistance measurement. Now, what is this dynamic on resistance measurement? Now, this is basically, that during a measurement, high power measurement, the device is kept under stress for some time before it is turned on. And by stress, it means that the non-quiescent voltage, the non-quiescent drain voltage is kept at a very, very high level before the device is turned on. Again, as we discussed before, the pulse timing in this case are very, very important. So we should take care that we don't create an intermediate stage that is harmful for the device. So here, the drain non-quiescent pulse is much wider than the gate non-quiescent pulse, which means that even if we create an intermediate stage, that is well within this safety limits of the setup. Now, in one of the papers, it is published the complete, the different characterizations of the dynamic on resistance measurement and what factors it basically depends upon. So it is reported that R on is, affected under two different conditions, which is, what is the R on right after the transition state. So as soon as the pulse turns on. So it means, the R on is measured at multiple timestamps within the pulse, and then the R on at different time states are compared. And the second is the time period of the applied stress, which means for how long the device was kept at a high drain non-quiescent voltage. Now for this results that were published in this paper, a very long pulse width was used. And now if we scan through the different timestamps within this pulse, we see that at 200 nanoseconds, which is right at the transition stage, the dynamic on resistance is very, very high. And at 10 microseconds, the on resistance starts decreasing. And at 10 milliseconds, it has stabilized itself very much. And the R on measured at 10 milliseconds is almost similar to the on resistance that is measured for the DC signal. So without the pulse characterization, which is the DC IV characterization. So which means that the R on is most effective, or is it's good to characterize R on right at the transition state. The next result that is published here is the applied stress, that how long the stress was applied and what were the results seen. So for this particular case, they applied the stress for almost 40 minutes. And we see that until 30 minutes, there is no significant change in the R on or the ID max. So we don't see any significant change until 30 minutes, but beyond 30 minutes, we see that the R on and ID max have significantly degraded. Similarly, here we see that until 30 minutes, right after transition, the R on was high, but after 30 minutes, it increased quite a bit. Similarly, for a different timestamp, which is 10 microsecond, it still keeps on increasing. And for 10 milliseconds, that is well within the stable region and well deep into the pulse, the R on is almost ineffective and almost same as the on resistance measured in the DC analysis. So another important application of a pulsed IV measurement system is the pulsed S parameter measurements. The principle of these pulsed S parameter measurements basically consist of superimposing the RF signal on each instantaneous bias point, and for each bias point within that IV network, an acquisition of the S parameter measurement is done. So this for this measurement, the pulsed IV system is synchronized with a vector network analyzer. The pulsed IV system acts as the primary trigger, and the delays within the vector network analyzers are, adequately used so that the pulsed S parameter measurements are always made within the stable regions within the pulse. So the choice of IF bandwidth and delay has to be very precise. In terms of vector network analyzers, Auriga supports multiple VNAs that include all Keysight and Rohde & Schwarz VNAs. Similarly, the measurement can be stored in different formats, in CT file, CSV formats, or the S2P format files. So here, it represents the graph, the entire graph of the graphical display of the pulsed IV measurements. We can see we have the IV characteristic curves, we have the time domain waveforms, we have the digital representation of each and every point, and we have the pulsed S parameter results. These S parameter measurements basically are the measurements that are done in the pulse mode, and they give the actual response of the device at each quiescent bias point. Now, another important application of pulsed IV measurements is compact modeling. So here, this figure basically represents the classical small signal HEMT model. So here we can see it is mainly composed of voltage controlled current source and some passive linear components. So the electrical model here, it can be divided into two different planes, the intrinsic plane and the extrinsic plane. So each intrinsic and extrinsic plane has a set of almost 8 elements. The intrinsic plane is basically used to model the active part of this device, and the extrinsic plane is used to model the passive part. The S parameter measurements, so for the compact modeling, both pulsed IV measurements and pulsed S parameter and pulsed IV measurements are required. So the pulsed S parameter measurements basically data, or the pulse S parameter that is measured, it models the linear response of all the extrinsic and extrinsic lumped element networks. So once this model is done, that is pretty much valid for all the small signal conditions. But for nonlinear analysis, we have to model all the nonlinear capacitances and the nonlinear current source. So the nonlinear capacitances are modeled over the assumed load line, while the nonlinear current source is purely modeled using the pulsed IV data. The Focus software suite, offers two different models to model the nonlinear current elements, which are the Angelov's nonlinear current source model and Tajima's nonlinear current source model. So now when we are talking about modeling, all the intrinsic and extrinsic parameters that we have to model, they can be tuned manually, or our software also allows optimization techniques. So here it's a small video that explains how each individual element can be tuned manually, or you can use the built-in optimization techniques. So here, once the optimization is complete, the results can be saved. Similarly, here it's represented one example of the current source model. So on the left is a figure where no optimization technique was performed, and on the right, it's with the optimization. So the IV curves for the generated model. So the Focus Compact model also offers a complete schematic or a complete information that can be exported to any of the simulation environment that includes both ADS and microwave office. A complete template is provided with the system. So here is an example of the simulated and the modeled data for the generated model. And finally, I will talk about some pulsed load pull system. You know, as we talked about the pulsed IV conditions, so in pulsed load pull, the pulse signal also plays a very, very important role when we are talking about large signal device characterization. So in large signal device characterization, you know, for high power devices, they might have some self-heating and memory effect issues that can severely affect the performance of or the performance of the power amplifier. So there, pulse signals, again, both pulse DC and pulse RF play a very, very important role. So with these pulse signals, you know, the device can be operated at higher peak levels. You know, we can control the temperature much better using these pulse signals. Also, the pulse signals become very, very important, you know, where huge heat sinks cannot be utilized. For example, when we are talking about on-wafer measurements, you know, for on-wafer measurements, heat sinks cannot be implemented. So the pulse signal becomes very handy in those conditions. Similarly, pulse load pull also plays a very, very important role when we are when we have to validate our compact model. So here I'll stop my presentation, and if you have any questions, please